Hello and welcome back, Fundamentals of Physical Geography. This is a really short video. I just want to give you a case study here to illustrate the way in which things from the module tie together. Different topics that you've covered at different points throughout the module, which you might have mistakenly considered to be isolated, separate topics or ideas, actually connect together. And that's one of the main themes of this module and of the whole of our degree program, in fact, that everything ties together. Reality is a bundle, not a list. So even though we necessarily learn things step by step, in the end what's really important is to be able to tie them together, see the connections between them, and thereby understand more fully how everything in the physical environment, in the natural world, is actually working. So the case study that I want to go through with you very briefly just now is just to tie together some of the ideas that we've talked about previously separately under the headings of plate tectonics, climate change, or climate, and landscape. And the key theme here is that there are connections between different topics within the module. That's a really important thing for you to take on board as you're finishing off your coursework, because there are connections between the different topics that make up physical geography. And so the idea here is just to bring together a couple of those separate topics that you've talked about previously. So we've talked about climate change in some detail. You had that in a previous step, and we've also talked about plate tectonics in a variety of different contexts. So let's just very quickly look at how we can tie those two together in a variety of different ways. How is plate tectonics important in the context of climate change? And also let's throw in, why not, let's throw in landscape as well, because we've talked a lot about geomorphology and landscape and the Earth's surface materials. How do Earth's surface materials and landforms and landscapes, how do they fit into that story of the connection between plate tectonics, climate, and climate change? So you're familiar, I'm sure, with diagrams like this. There's a map showing the Earth, well, showing some of the Earth's surface plates, so you understand all about the lithosphere being broken up into these separate sections that are moving relative to one another. And there are processes and geographical patterns associated with all that. You're familiar with that. So here, for example, just a series of maps from 250 million years ago, 150 million years ago, and the present day, just illustrating one of the issues that is fundamental to the idea of plate tectonics, which is the idea that the continents change position over the course of time. So the distribution of the continents and the oceans isn't fixed, it changes through time. The geography of the planet, the basic geography of Earth, is constantly changing, and the continents, the oceans have moved around, they've opened up, they've closed down, they've met, they've crashed, they've separated again, repeatedly over the course of Earth's history. And you're familiar, as part of that plate tectonics system, if you like, with the idea of divergent plate boundaries, convergent plate boundaries, transform boundaries, and all the various landforms and processes that are associated with those. So you're familiar with continental collisions and subduction and mid-oceanic ridges and intraplate hotspots and the Andes rising up where the oceanic plate is being subducted beneath the west coast of South America. You're familiar with all that kind of background under the heading of plate tectonics and landscape. The question is, for today, well, how does that relate to everything we've been saying about climate and climate change? What's the relationship between plate tectonics and climate? Well, here's a quick summary of just a few points. Again, remember, you can pause the video, come back, go through this list later on and tick off boxes and find examples and case studies and illustrations of your own. But there are just a few headlines or headings there that you could use maybe if you were doing, suppose you were planning an essay under this title, how does plate tectonics affect climate? Well, just think about what the controls are on climate, both at a global scale and at a regional scale. And some of the biggest things that you think about when you're talking about what are the controls on global climate, well, you might think, for example, about atmospheric composition, the composition of the atmosphere. That's one of the big things that controls climate. How much carbon dioxide is there in the atmosphere, for example. That's a major control on global climate. Another big control on global climate is the arrangement of the continents, and we've encountered that in a variety of different contexts previously in the course, and I'll say more about that in just a second. But the arrangement of the continents, where the land masses are, where the oceans are, where the ocean can get through gaps between continents, whether there's land at the poles or whether the poles have deep oceans on them, those are really important controls on what's happening to the climate globally. At a regional scale, well, you can pull out things such as atmospheric circulation. Where's the jet stream going? Is there a jet stream? How's the atmospheric circulation working? Well, that will determine where you get different types of climate around the planet at particular latitudes, depending on that atmospheric circulation. And also, and connected with the atmospheric circulation, of course, the oceanic circulation. Another big control on regional climate is altitude. And so plate tectonics, affecting altitude, uplift of areas, gives you areas of higher land, areas of lower land, and that has an impact on climate. And that's really what the third heading there is all about. We've seen here some of the controls on global climate and on regional climate, and we say, well, what does plate tectonics affect then? What could that be influencing? And you'll see I've filled in there basically all of those headings from some of the controls we've listed on global and regional climate. Well, those are listed there as being things that plate tectonics can affect. Plate tectonics affects atmospheric composition. It affects the arrangement, the position of the continents and the oceans. Plate tectonics affects the atmospheric circulation, where the jet stream's going and so on and so forth. It affects ocean circulation, and it affects uplift and therefore the altitude of different places on the Earth's surface. So let's look at those in just a little bit more detail, and some of these we've already seen, you've already covered some of these. So this map here showing the global ocean conveyor belt, the thermohaline circulation of the ocean with which you're familiar in its current configuration, and that current configuration is controlled by partly the positions of the continents and where the currents can find its way between continents. And we've talked previously about the Panama Gap and the fact that when that gap between North and South America closed, that had a major impact on global ocean circulation, separating the Atlantic from the Pacific and closing off that connection between the two, leading to a major change in ocean circulation that itself then had major climate impacts. And we said earlier in the module how that closure of the Panama Gap could well have been one of the major contributory factors towards the initiation of our Quaternary era, the Quaternary Ice Ages, this period when we've had colder and much more variable climate than in the period prior to that when the Panama Gap was open. There are lots of different factors that are contributing to our current ice age, but that Panama Gap, driven by plate tectonics, closing that gap between North and South America, is certainly one of the likely candidates for being a major cause, a major controlling factor on that climate change. We've also made the point previously about how the positions of the continents plays a major role in global climate, because in order to initiate an ice age, it's much easier or much more convenient if you have a certain disposition of continents. So right now, one of the things which helps our current ice age to persist is that we have a land mass at the South Pole, in the Antarctic, and we have a shallow ocean surrounded by land at our North Pole, in the Arctic. If both poles, in other words the parts of the world where you get least solar insolation, so the coldest parts of the planet, if those are over deep oceans, then it's very unlikely that you'll get ice masses forming at the poles, because of overturning, heating, circulation of the water will prevent ice from forming. But if you have a shallow ocean, such as in the Arctic, surrounded by a land mass, or if you have a continent, such as in Antarctica, well, those conditions are much more favourable for snow settling on land. So snow settling on water melts and you lose it. Snow settling on land can settle and can build up. Or if you start to freeze the ocean surface, if it's a shallow ocean with lots of water flowing into it, surrounded by land masses and low salinity or fresh water flowing into that closed basin, much easier to freeze that water than if you have a deep salty ocean at the pole. So you're much more likely to get snow on land or ice on water with this current continental disposition. Once you get ice on the water or snow on the land, well, then there's a positive feedback effect through albedo, because the reflectivity of the Earth's surface increases as you increase the whiteness, the snow or the ice on the surface. So by having the continents in just the right position, you can encourage and generate these positive feedbacks that support the development of an ice age. So the positions of the continents driven by plate tectonics, really important in controlling what kind of climate changes are likely to be sustained and to be amplified. Another of the big factors that we've talked about in terms of plate tectonics and that we can relate to climate is the formation of the Earth's major mountain belts. Get your atlas out and have a look at where the big mountains are, and then compare that with your map of plate tectonics and convergent plate boundaries and so on, and you'll see, for example, we can pick out on here, for example, some of the big ones. The Himalayas, the Tibetan Plateau, where you have converging plates, the Andes in South America, and the Rockies mountain chain running up the west coast of North America. These major mountain belts, particularly the Himalayas and the Tibetan Plateau, have a major impact on the world's atmospheric circulation. The way the jet stream works, the way lots of the major atmospheric circulation systems work, is to some extent modified or controlled by the positions of these major upland areas, which are themselves, the positions of those are determined by plate tectonics. So you can think, for example, about the monsoon circulations, the climatic phenomena associated with that. And at a very basic level, the idea of rain shadows. If you have mountains close to the coast, for example, then you generate rain shadow effects with deserts potentially behind the mountains, and enhanced rainfall on the coastal side of those mountains. And if those mountains get high enough, then instead of talking about rain falling on the mountains, then we start talking about snow falling on the mountains. If the mountains are high enough, we get snowfall. And as we talked about previously in the module, once you get snowfall, that's a major interruption to the hydrological cycle. If that snow builds up on land year after year and turns into glaciers, then we have a major storage point in the hydrological cycle. We also have, like I talked about before, a major impact on albedo, so positive feedback. And once you start getting snow and glaciers, then you're likely to get more snow and glaciers, and that's going to have a feedback effect on the climate. And that also, once you get snow and glaciers on an uplifting mountain chain, well, even if you think back to what we talked about with W.M. Davis earlier on, uplift followed by denudation, and if you've got glaciers on a mountain, you're going to have plenty of denudation. Well, that leads through to the follow-up slide to this one. We're just going to move on. Atmospheric circulation, monsoons, rain shadows, snow line, glaciation, albedo. Well, glaciation, erosion. If you have an uplifting mountain chain and you have even just rivers or glaciers acting on those, you're getting lots of erosion. That erosion is picking material up in the mountains, carrying it down, moving it towards the oceans. That ground up rock material being carried in the rivers or deposited at the edges of glaciers, that's very susceptible to weathering. If you have a great big lump of rock, that's going to be quite hard to weather. It's like having a great big cube of sugar. It doesn't dissolve instantly in your cup of tea. But if you grind it up into little grains, if you have sand, dust, silt ground up from this rock, just like having individual grains of sugar rather than one great big lump of sugar, it's much more susceptible to chemical weathering. And envisaging the solution of sugar into your hot cup of tea, that's quite a good analogy for thinking about some forms of weathering. Solution is a form of weathering. And so if you wanted to weather this rock, it can be weathered much more effectively once it's separated from the bedrock, and even more so once it's then broken down into finer grained components. And that's important because weathering has a big impact on climate, because weathering is essentially a set of chemical reactions. And those chemical reactions do all sorts of different things. You've read up on weathering previously in the module, so you know a little bit about weathering. But in a very general kind of a way, we can say that if you combine the different kinds of weathering that are going on in Earth's surface environments, they typically involve what we call the drawdown of carbon dioxide, of carbon from the atmosphere. So weathering reactions use up carbon dioxide. So there's an impact on the characteristics of the atmosphere depending on how much weathering is going on. If you have lots of erosion by glaciers, say, comminution, breaking up of rock into smaller and smaller fragments and exposing them to to moisture in the environment, then you're going to have enhanced weathering, and that's going to have a bigger effect on the atmosphere. So plate tectonics can influence climate by making mountains to create erosion, to open up the possibility of more weathering, which then affects the atmospheric composition. And as you remember from earlier in the course, once you have changes in atmospheric composition, well, that has all sorts of impact for the radiation budget, for example, radiation in, radiation out, chemicals in the atmosphere, carbon dioxide, etc., in the atmosphere, making a big difference to those interactions. So plate tectonics affecting climate there in a complex and interesting way. Also, other more direct ways in which you, hopefully now from what I've just talked about before, thinking about atmospheric composition and thinking about the processes that are associated with plate tectonics, you may well have started to think there about, well, more direct impacts of plate tectonics, volcanic activity on the atmosphere and therefore on climate. And this slide just kind of notes for you a few points for you to do a little bit of reading up on there. The release of carbon dioxide, for example, by volcanism and seafloor, spreading sulfate, aerosols, dust going up into the stratosphere. You're changing the composition and characteristics of the atmosphere, and that can have all sorts of different effects, whether it's blocking insulation, physically blocking insulation, or changing the greenhouse effect as a result of changes in CO2 and other chemicals in the atmosphere as a result of that volcanic activity, which is itself a result of plate tectonics. And I've just listed for you there a number of volcanoes, some relatively recent, Pinatubo, Krakatoa and Tambora. They're just for things for you to go and look up, some fairly major volcanic eruptions during recent history. Tambora 1815 is the biggest of the three, and the most interesting from our point of view in terms of its direct and significant impact on climate. People refer to the year without a summer which followed the eruption of Tambora, as a result of its impact on the atmosphere globally, and it led to famines and all sorts of problems around the world, but it had a major impact on climate. And by comparison with the two I put at the bottom of the list there, the Columbia River flood basalts and the Deccan traps, which were periods of volcanic activity and areas of volcanic rock which were produced during those activity in the northwest part of North America and in India. Those flood basalts and the Deccan traps flood basalts again, those created huge impacts on climate that, if you read up on the Deccan traps, for example, there are arguments that those were involved in or played an important role in the decline of the dinosaurs because of their impact, the impact of that volcanic activity on global climate. So there are major controls there of climate coming from significant volcanic activity resulting from plate tectonics. So I've deliberately, I know I've rattled through that at a great rate of knots. I didn't want to linger on things. I just wanted to make the points that there are these connections. If this is something you want to read up on and do more, get more information about, then hopefully there was enough in the headings that I've given you that you can go away and do some reading on that. And just to summarise there, plate tectonics affects climate in all sorts of different ways, but for example, by releasing CO2 and aerosols into the atmosphere, directly changing the atmospheric composition. Second, by changing the position of the land masses, and that can have a number of effects, for example, setting off glaciation either regionally or globally, and also by changing ocean circulation. And the one which I guess is interesting as a case study to combine plate tectonics, climate and landscape, the geomorphology that we were talking about previously, this idea that plate tectonics causes uplift, step one of Davis's cycle if nothing else, but plate tectonics causes uplift, which then affects climate in a variety of ways by raising land above the snow line. So you get snow, you get glaciers, you get albedo feedbacks, positive feedback on glaciation. That glacial activity then initiates enhanced erosion. That erosion produces material that can be subject to enhanced weathering. That weathering then impacts on atmospheric composition. The uplift also has had an impact on the atmospheric circulation. So there's lots of different things going on and interacting in there. And that's kind of the theme for this week. And if you're doing your patchwork assessment based on what we're covering this week, I suggest that you could pick up plate tectonics, or you could pick up coasts if you want, but really the point of these examples that we've given you this week isn't coasts or plate tectonics or climate or any other single topic. It's connections between different parts of the module, connections between different things in physical geography.